Have you ever stopped to think about how your phone actually works? I mean, really think about it. How, in a stadium packed with thousands of people, can you pull out your phone and just make a call? It feels like it should be impossible, right? Well, it's not magic. It's an absolutely incredible, invisible feat of engineering. So let's pull back the curtain and see how it's done.
Right, let's stick with that stadium example. It's the perfect way to picture the problem. You've got tens of thousands of devices all in one place, all trying to talk at the same time. How is it not just a chaotic mess of static? How does your call get through, clear as a bell, when so many others are happening right next to you? That is the fundamental puzzle that engineers had to solve.
And the heart of that puzzle comes down to one simple fact. The airwaves are not infinite. This thing we call the radio frequency spectrum, it's a limited resource. Think of it like a highway. There are only so many lanes. Trying to get every phone call onto that highway at once is a recipe for a total gridlock. This is what we call the spectrum squeeze, and managing it is everything.
So how do you prevent that gridlock? Well, you need a really smart set of rules. You have to bring order to that potential chaos. And that's our first stop. Let's look at how the airwaves are organized, the basic rules of the game. It all starts with this number. In the original analog cellular system, the one that started it all, the entire thing was built around 666 distinct channels. That was it. This was the blueprint, the first real attempt to slice up the airwaves into usable lanes for our calls to travel on.
Now, when we say channel, it's not just one single frequency. It's actually a pair. This is a concept called duplex operation. See, you need one frequency to send your voice to the cell tower, we call that the uplink, and a totally separate one for the tower to send stuff back to you. That's the downlink. And they're kept 45 megahertz apart on purpose, so your own voice doesn't interfere with what you're trying to hear. Pretty clever.
And here's something you might not know. Not all of those channels are even for talking. The huge majority, almost 94%, are what we call voice channels. But that little slice, just over 6%, those are the control channels. Think of them as the network's traffic cops. Their only job is to manage the network and set up your call before you even say hello. They are absolutely critical. To make things interesting and, encourage some competition, the whole spectrum was split into two big chunks, Block A and Block B. A city would typically have two different carriers, one for each block. And as you can see, each one got their own set of channels to play with, 312 for voice and 21 for control. The setup made sure they wouldn't step on each other's toes. Okay, so the channels are all neatly divided up. But how does your phone actually grab one when you need to make a call? Well, that brings us to the next part, the playbook. There are two main strategies the networks use to hand out these channels, and they're pretty different. Let's just define our terms real quick. Channel assignment is pretty much what it sounds like. It's the brain of the whole system, the process where the network decides, okay, for this specific call, from this phone, in this location, you get this channel pair. It's happening in a blink of an eye all the time. So there are two main ways to think about this. First, you have fixed channel assignment, or FCA. I want you to think of this like reserved parking spots. Each cell tower has its own dedicated set of channels. It's simple, it's predictable. But what happens if all its spots are full? The other way is dynamic channel assignment, or DCA. This is way more like a valet parking system. All the channels are in one giant pool, and the network can assign any free channel to any tower that needs it, right on the spot. It's super flexible, but as you can imagine, it's a lot more complicated to run. And that brings us to the big question about that simpler fixed system. What does happen when you try to make a call, but all the reserved spots for your local cell tower are already taken? Does your call just fail? Do you just get a busy signal? Well, not always. This is where a really slick workaround comes into play, a borrowing strategy. If a cell tower is maxed out, it can actually ask a neighbor that isn't as busy if it can borrow a free channel. And the whole loan is supervised by this central brain called the Mobile Switching Center, or MSC. It's the air traffic controller for the entire network, making sure these handoffs happen smoothly. So if that dynamic valet system is so flexible, why not just use it all the time? Well, here's the catch. To make that system work, the network needs a ton of real-time information. It has to know exactly which channels are being used, what the signal strength is, where every user is, and it has to know it for every single cell, all at once. all of that data crunching creates a huge computational load, making it way more complex than the simple fixed system.
But life isn't always random, right? Some traffic jams are predictable. Think about rush hour. For situations like that, the network can't just react in the moment. It has to be proactive. It needs to be able to call an audible, just like a quarterback at the line of scrimmage.
And the classic example is the rush hour problem. Traffic flow is not even. In the morning, you get this massive wave of people commuting into the city and all the cell traffic spikes downtown. Then, in the evening, that wave reverses and heads out to the suburbs. A simple static network would just get overwhelmed by that predictable one-way surge.
So engineers came up with some brilliant solutions to handle these daily surges. 3 of the coolest tricks in the playbook are the underlay-overlay arrangement, which basically splits a cell into 2 zones, intelligent frequency assignment, which uses algorithms to get ahead of demand, and even physically tilting the antennas on the cell towers to reshape where the signal goes.
Let's just zoom in on that first one because it's genius. With an underlay-overlay, you take a single cell's coverage area and you split it in 2, a small inner circle and a larger outer ring. By giving each zone its own set of frequencies and running them at different power levels, you can basically cram twice as many users into that busy area without them interfering with each other. It's a fantastic way to boost capacity, right where you need it most. You know, when you take a step back and you look at all these different pieces, the channel assignments, the borrowing, the traffic management, you really start to appreciate the whole system. It's truly one of the unsung marvels of modern engineering that just works every day. And that's really the main takeaway here. We started with a huge problem, a very limited amount of space in the airwaves. And from that, we've built a world where millions of clear, simultaneous connections are possible. It's all managed by this incredible, invisible, high-speed dance of algorithms and rules that's happening constantly, right under our noses. At the end of the day, all of this complexity, all this genius engineering, it boils down to one simple mission. The ultimate goal is just to make sure that when you want to make a call, you can. It's all about making the chance of your call getting blocked as low as humanly possible, no matter where you are or how busy things get.
We've come so far, from those first 666 channels to the incredible complexity of today's 5G networks. That invisible dance has only gotten faster and more intricate. And it really makes you wonder, right? As our world demands more and more data, faster speeds, connections for everything from our watches to our cars, what's the next great leap in managing our airwaves going to look like?